Hello everyone, and this is an introduction to cosmology. And cosmology is the study of the universe as a whole. And the universe is everything that exists, and another word for it is the cosmos. And so we're going to look very quickly now at the universe from the Big Bang to the solar system, at least as far as we know. So, the Big Bang was the beginning of time. And we have to bear in mind that time is part of our model of physics, and before the Big Bang, our model of physics didn't work. But the Big Bang was 13.7 billion years ago, as far as we understand it, and it may have been an expansion from some kind of quantum fluctuation or bubble, a bubble of possibility which was suddenly able to become a reality for some reason. And this led to a violent expansion. All energy and space was created from a single point in a single instant of time. And this origin point for the expansion is called a singularity. But there's nowhere in the universe now which is the point of the singularity. All of space was there at the singularity, and all of space is still there. It's just a lot bigger now. Some of these ideas can be a little bit mind-bending, and I invite you to just go with it for now, and you can sort of get more understanding over time. So, speaking of time, we divide our ideas of cosmologic time into epochs, or epochs, and an epoch is a period when the universe is in some kind of state, a certain type of energy or maybe particles dominating. A new epoch signifies some massive change in the overall state of the universe. So, if we look at a timeline of the Big Bang was the beginning, and then there was the Planck epoch, and physics is still unable to do anything with this because the Planck time is in the order of 10 to the minus 34 seconds, and any time that's shorter than that cannot be analysed by physics. It is the shortest time that physics is able to deal with at the moment. So even though the Planck epoch was after the Big Bang, we cannot actually do anything to understand it. Then there was the Grand Unification epoch, where all the forces we now know were combined into one force because of the intense environment of that time in the universe. After the Grand Unification epoch came the inflationary epoch, when the strong nuclear force split off from the other forces, and this triggered, we think, a massive expansion to a size of around 84 million light years for the universe. And then the electroweak epoch following that, and then the quark epoch. The electroweak force now divided into the weak nuclear force and the electromagnetic force, which we all know from daily life. And the universe at this time is called a quark-gluon plasma. There are many subatomic particles flying around in this hot, dense state. And then finally, the quarks began to come together to form protons. They began to form hydrogen nuclei, and a proton is a kind of hadron, and so we entered into the hadron epoch, where protons dominated the universe, and subsequently neutrons as well. So how long do you think all of this took until the end of the hadron epoch? It took about 1 second. Yes, that's right. All of those epochs happened in the first second of the universe. So, the Big Bang was t equals 0, the beginning of time. The Planck epoch was in the order of 10 to the minus 43 seconds. Like I say, shorter than the Planck time. And once we get past the Planck time, we're into the Grand Unification epoch at around 10 to the minus 36 seconds. And the inflationary epoch followed on with the electroweak epoch, and I would just like you to remind yourself that the universe expanded to a size of around 84 million light years across in 10 to the minus 32 seconds. So this actually is faster than the speed of light, but the speed of light is only a speed limit inside the universe. At this time, it was the universe itself was expanding at faster than the speed of light, much, much, much faster than the speed of light, and there are no rules on how fast the universe expands that we know of. So then, by the time we got to the end of the Hadron epoch, or the quark epoch, we were in the order of 10 to the minus 3 seconds. So now we're coming to more everyday measures of time. And so by the end of the Hadron epoch, we were looking at a time of around 1 second. And around that time, we were experiencing the first apocalypse. So there was a lot of destruction going on at that time. Matter and antimatter were coming together and annihilating. When matter meets antimatter, they destroy each other. So at first, it was protons and antiprotons, and that ended the Hadron epoch. They all wiped each other out, or almost. And then smaller particles like electrons and positrons, which are anti-electrons, annihilated with each other. And for some reason, there was slightly more matter than antimatter. We don't know why, and that is the only reason that there is any matter in the universe right now at all. Otherwise, it would all just be energy. Then we got into the cosmic dark ages, and this was when the universe was about 3 minutes old, until it was about 400,000 years old, so they lasted for quite a while. So this was a time when photons existed, but they were part of an interacting plasma, and they flew in around other particles, bouncing off them and generally not getting very far. So light did not really exist at this time. We couldn't use photons to see by. Obviously there were no beings to see anything then, but even now we cannot record those photons from the Dark Ages and use them to tell anything about that time. So it's not possible to see light at that time. So now we're up to around 10 to the 5 years after the Big Bang, and that's the end of the Dark Ages, and here is where the universe had cooled enough to allow hydrogen and helium nuclei to capture electrons so they could form the very first atoms, and that meant that matter, as we see it every day, now existed, although at the beginning it was only hydrogen and helium. And this is called the epoch of recombination, when those electrons were captured when they combined with the protons and neutrons to make atoms. The photons from that time have now been traveling through space ever since then. When the electrons got bound to the nuclei, the photons could then fly through space and not interact. And the light from that time is something we can still detect, and we call it the cosmic microwave background, or cosmic background radiation. And for example, the static on your TV screen when you get that grey fuzz is at least partly due to the cosmic microwave background radiation. So, like I said, at first the universe was simply hydrogen and helium, but now gravity could start to take some serious effects, and it started to pull hydrogen and helium atoms together. And more atoms in one place have more gravity, so they started to pull in more atoms. And at last there was so much density at the center of this cloud of hydrogen and helium that a nuclear reaction ignited, and that caused the very first star to be born. It was not alone for long, I'm sure. All over the universe, hydrogen was clumping together, and its gravity was eventually forming a nuclear fusion reactor in space. And over time, the universe lit up even more. So other stars started to form, and those stars under gravity started to come together, and that meant that we ended up with galaxies started to form as hundreds, and then thousands, and then millions, and then trillions of stars began to orbit each other in spinning masses. And galaxies are where stars for the most part live, and they are centered around a galactic core, and in the middle of a galactic core you will find a supermassive black hole, but let's not go there right now. In fact, let's not go there ever. That sounds like a terrible idea. So our solar system formed about 4.6 billion years ago, and just like before, it started with a huge cloud of hydrogen in a nebula somewhere. But because our sun was not one of the first generation of stars, other stars had died before it, there were some other elements in this cloud. It was not just hydrogen and helium, although it was still mostly those two elements. Over time, gravity pulled it together, and it got hotter, and it got denser, and it started to spin, and eventually it got so dense in the center that the sun was born, and there was a hot spinning disk around it, because not all of that material had been pulled into the sun, and some of it was still spinning around the outside, and some of it had been blown away by the pressure coming out from the newly born sun. So the disk condensed under gravity as well, so all of that material started to come together under gravity, and then it started to ball together into spheres, and so eventually these rings around the sun clumped together to form all of the solar system bodies, so all of the planets that we are familiar with. So there's a couple of misconceptions we need to clear up about the Big Bang. It was not an explosion. Sometimes it's natural to kind of think of it as an explosion. It was very hot and it expanded very quickly. But in reality, what was happening was the universe was very small, and all the matter was still there, all the energy, and a lot of matter in a very small space is very, very, very hot. So don't think of it like something bursting, a popping balloon releasing energy. It's more like a balloon being stretched as you blow it up. The rubber in the balloon gets bigger. There's still the same amount of rubber there, but it's spread over a larger area. So the other thing is the singularity was not somewhere in space. So space-time began with the Big Bang. There was no space or time before that. So as I said before, there's nowhere you can go in the universe today and say, this is where it all started from. That place is everywhere. If there ever was anything outside the singularity, or still is, we don't know anything about it, and we have a few theories, but there's nothing that's been really seriously proven. So, how the hell do we actually know all of this? Well, this is one reason. This is the Hubble Space Telescope, and it's been one of our greatest champions for discovering the cosmos. It was launched in 1990, and it can see much further and much deeper when there is no atmosphere to look through. Of course, we still use telescopes on the Earth because we can build them so much bigger, and that helps. But when you don't have to look through the atmosphere, like Hubble doesn't, you can look much further and much deeper than before. So Hubble is getting quite old now, and in 2018 the James Webb Telescope is due to go up. So that's been being built for many years now, and it's finally going to be ready in 2018. But Hubble is still going to be useful, and it could be looking out at the universe until 2030, or who knows, even beyond. So we'll have a quick look at some of the evidence for the Big Bang, and These pieces of evidence are to be taken as general support, but there's no real silver bullet piece of evidence that proves the Big Bang. We're fairly sure that something happened 13.7 billion years ago, but we haven't actually demonstrated exactly what it was. So one thing we do know is that the universe is expanding, and it was Hubble that showed us that using something called Redshift. Edwin Hubble measured that most galaxies are moving away from us and from each other, and in fact the farther away they are, the faster they seem to be moving. And with Redshift, you may know that white light is made of all the other colors of light, and the color of light is dependent on its wavelength, and red light has a longer wavelength than blue light, and this is the important point about redshift. Light waves can be stretched as they travel through space, and if it's stretched, that means it's going to become more red because the wavelength will increase. That might be a bit of a hard idea to get your head round, but we can look at an example from sound. So, what is redshift? To answer that, let's talk about the Doppler effect. So, if you've ever been on the street and a police car has passed you with its sirens going, the noise changes as it goes past. I'm going to try and do an impression of that now, so please forgive the noise. The police car will sound something like it will change sound as it goes past you. The sound will actually go down, it will get lower. So sound waves are affected by movement, as can be shown by these diagrams below. In the diagram on the left, you can see that as the red dot moves, emitting sound, the sound waves in front of the object are squeezed up because the sound catches up with itself in a way, and behind the object they are stretched out as the sound is stretched out behind the moving object. In the diagram on the right, you can see that a stationary object emits sound simply as concentric expanding waves in all directions. So sound at lower frequency will get lower. That is why after the police car goes past you, you are hearing those stretched sound waves, and you're hearing them at a lower frequency. The same thing happens with light. But when light goes to a longer wavelength or a lower frequency, instead of getting lower, it gets redder. So when objects are moving away from us, the light gets stretched, and so objects that are further away seem to be getting redder. But this effect is not seen at normal speeds. Technically, I suppose it happens, but there's no way that you could measure the redshift on somebody running away from you, for example. So, background radiation is actually another piece of evidence for the Big Bang, because the oldest light in the universe comes from that time, the era of recombination, or the epoch of recombination. So when those atoms formed, you may remember, plasma became matter, and that meant that photons stopped interacting with it and began to fly straight through the universe. And those photons are still traveling now, and we can detect how long they've been traveling, and we can tell that they were once very high energy photons that have dimmed over the course of their journey. Quasars is a very sci-fi sounding name, and these are solar system sized galactic cores, and they put out more light than whole galaxies at a time. Quasars are very high energy objects, but they are also more common earlier in the universe, and this showed that the universe was changing over time, that long time ago there were more quasars and now there are less. So this was not so much evidence for the Big Bang as it was evidence against the idea that the universe stayed the same, the steady state universe as it was called. This was a very popular idea for a long time, and this idea that quasars were more common once upon a time was a big problem for the steady state universe. It clearly showed that things were changing. We can also look at radioactive decay. We know that radioactive elements decay at a predictable rate, so we can tell how old rocks are. And moon rocks have been found and dated to be older than the Earth, and this gives us at least some confidence of how the solar system formation went. And that means we have a consistent time of around 4.6 billion years, and we know that the Sun was not a first-generation star, so the timeline that's emerging from the radioactive decay we can detect seems to be consistent with a universe that is at least in the ballpark of the age we expect. So I just mentioned that we can use stellar formation and evolution and our understanding of the life cycle of the stars to understand how that might impact on the development of the universe and what might that tell us about the age of the universe. So our current models of stellar evolution show that generations of stars seem to match our expectations. And again, it's building up a general picture of a universe that is of the age we expect. Finally, the speed of light can help us. The speed of light is a universal constant, we know, of around 300,000 kilometers per second. And we observe stars millions or billions of light years away, and as we know, a light year is the distance that light travels in one Earth year. So if a star is 500 light years away, the light you see today left the star 500 years ago. Those photons have taken 500 years to get here, so you really are looking back in time when you look at the stars. And the furthest stars we can see are 10 to 15 billion light years away. And we have equipment that could see further than that, but there isn't anything viewable. Notice that it's important not to say there isn't anything there. There might be something there. We can see what is called the observable universe, but the universe could be much bigger than that. The problem is that light can only have been traveling since the era of recombination. And so that tells us that if the furthest stars that we can see are 15 billion light years away, that doesn't mean that those are the furthest stars that there are. It just means that's the longest time that light has had to travel to get to us from those stars. And anything further away, there has not been time in the universe for the light to get here. And so that's it for our brief look at cosmology, and I'd like to just point out the background to this slideshow, which is a section of the Hubble Deep Field, as it was called. And back in the early days of Hubble, we were testing out its capabilities, and so we took it and we pointed it at the darkest piece of sky that we could find. So we picked an area of sky that we knew, as far as we could tell, had nothing in it. And we took an image from that section, and this is what that image contained. And so, to be clear, everything you see in this image is not a star, it is a galaxy. So, some of the large objects are very obviously galaxies, but even the tiny points of light, those are not stars, those are galaxies, each containing billions or trillions of other stars. The universe is big, and it was Hubble that allowed us to see it for the first time. Both the man, with his ideas about the expansion, and the telescope, which allowed us to see this kind of fantastic image, which really blew astronomers away back at that time. So, I hope you've been a little bit blown away by this. Cosmology is that kind of subject, but we're trying to find out more about it every day, and I hope you've learned something. Bye-bye for now.